Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss how to find maximum and minimum values of functions. If you remember, in a previous lecture, we discussed about increasing and decreasing regions and how to find them. It appears we can find the increasing and decreasing regions of functions using their derivatives. So if you look to this region, the red region, you can see that the function is decreasing. And if we draw the tangent lines onto the points in that region, we can see that the slopes of those tangent lines are negative, or essentially the derivative of the function at these points are negative, because we know that the slope of a tangent line is nothing else as the derivative of the function at that particular point. And if you look to this blue region, the function is increasing, and the slope of all of the tangent lines for all of the points in that region are positive. So the k is positive, or the derivative of the function is positive. So by just identifying the signs of the derivative of the function, we can identify increasing and decreasing regions. So our purpose for this lecture is to identify this point, actually, in particular, this red point, where the tangent line is going to have zero slope. So essentially, the derivative of the function is going to be equal to the zero at this point, here at this point. Okay, so we call this point in particular as the local minimum point. So any point where the function was decreasing before this point and then increasing after this point is going to be called as the local minimum. And at the point of local minimum, the tangent line is going to be simply horizontal. At the same time, the point is going to be called local maximum if the curve was increasing before that point and then decreasing. Okay, so our goal is first of all identify the local minimums and local maximums. So first of all, we define what is the local minimum and local maximum. Local minimum is the point, right, the height of the point, height of the function, where the function was decreasing first and then increasing. And the local maximum is the point where the function was increasing and then after this point was decreasing. So in this regard, it is very important to state the Fermat theorem, so which states that, hey, if f of x has a local maximum or local minimum at some point c, then the derivative of the function at that point is equal to the zero. So essentially, the tangent line is going to be horizontal. So what we need to do is we need to look for the points where the derivative is equal to the zero, right? And also then we need to look to the signs of the derivative. Okay, so let's try to do this for this function. So find the local minimum and local maximum for this function. In order to do this, we first of all are going to take the derivative of this function. The derivative of this function is going to be equal to the 12x in the power of 3 minus 48x in the square plus 36x. So I'm going to take out the x from the brackets, or 12x from the brackets can be taken out. So the 12x. And what is left inside is x in the square minus 4x plus 3. So we can factorize this term as well. So what we can do is, it is going to be 12x times the x minus 3 times the x minus 1. So there are a couple of points, or essentially 3 points, where the derivative is equal to the zero. They are. So the derivative of the function is equal to the zero at the point 0, right? If you substitute 0, you're going to get 0. Or the derivative of the function is equal to the 0 at the point 3. Or the derivative of the function is equal to the 0 at the point 1. So in order to find whether this point is local minimum, or this point is a local minimum, or this point is a local minimum, we need to look for the signs of the derivative. So we are going to put the number line, we're going to put all of these points in the number line. So it is going to be 0 here, 1 and 3. 3, 1 and 0. And then we need to look for the sign of the f prime of x. So well, if you choose any point which is greater than 3, this function here is going to be positive. So I'm going to put plus. Then if you put any number in between 1 and 3, it's going to be negative. then positive, then negative. If you remember, the signs of the derivative is going to tell us whether the function is increasing or decreasing. So for all of the points from minus infinity to the 0 up to 0, the function was decreasing because the derivative is negative. Then it is increasing, then it's again decreasing, then again it's increasing. Okay? So derivatives are equal to the 0, or the tangent lines are simply horizontal at the 3 points. But the function is going to have the local minimum at this point, right? And at this point, and it's going to have the local maximum at this point. So it's going to be the local maximum. At this point is going to be the local minimum. And this point is also going to be the local minimum. Because if you remember, local minimum means the function should decrease before this and increase after this. And local maximum means the function was increasing before this point and decreasing after this. Okay, so if you look to the curve, it is going to look like essentially like this. So the function, so this point 1, right, at the point 1, the function is going to reach its local maximum, and at this point 3, the function is going to reach its local minimum essentially. So here at the point 0, the function is going to reach its local minimum again because it was decreasing. So this is essentially the curve, the graph of this curve. So what we want is, we would like to do further analysis in order to try to understand whether the inverse statement is correct. So the Fermat theorem tells us that, hey, so if you've got a point, and if you know that this point is local minimum or local maximum, then the derivative is equal to the 0. But actually what we want is, we would like to find local maximum and the local minimums, right? So essentially, we know how to find the derivative of the function, right? And we know how to find the zeros of the derivative of the function. But essentially, so we have to use this fact in order to find the local maximum and local minimum. So the question is, if the derivative is equal to the 0, does it mean that this point is local maximum or local minimum? That's the question, right? Do you feel that this is the inverse statement? So the Fermat theorem tells you that if you've got local minimum, then the derivative is equal to the 0. Now we're asking, if the derivative is equal to the 0, is it local minimum? So it appears no. So sometimes, even though the derivative is equal to the 0, we're not going to have neither local maximum nor local minimum at that point. For example, if you've got this curve x cubed plus 3, we can find at the points where the derivative is equal to the 0. So let's find the derivative of this curve. The derivative of this curve is going to be equal to the 3x in the square. If you equalize this to the 0, you're going to get simply x is equal to the 0. So essentially, when x is equal to the 0, f prime of x is going to be equal to the 0, right? The question is, so at this point 0, the derivative is equal to the 0, right? At some point, derivative is equal to the 0. Does it mean that f of 0 is local minimum, right? This is the question. So it appears no. So we can see this from the signs of the derivative. So if you would put the signs, so it's going to be 0. So the function, the derivative of the function is going to be positive before and after. So essentially, it is increasing before the 0 and also increasing after the 0. So it means that it is not neither local minimum or local maximum. And we can see this from its graph as well. So if you sketch the graph of the y is equal to the x in the cube, you can see here that at this point, when x is equal to the 0, y is equal to the 1, right? The tangent line is going to be horizontal, but we can see this from the graph that this point is not local minimum, right? Or neither local maximum. So essentially, the statement doesn't work for the inverse direction. But also, it is there is one more question is, like Fermat theorem is again tell us that, hey, if you've got local maximum and local minimum, then the derivative is equal to the 0. And then again, the question, or also it says that the derivative should exist. What happens if derivative doesn't exist? Does it mean that it is not local maximum or local minimum? So again, so if you've got a point for your function where derivative doesn't exist simply, does it mean that this point cannot be minimum or maximum. Again, this is false. So false doesn't mean that it is always true, by the way. So false means that if derivative doesn't exist, it might be minimum point or maximum, or it might not be. Okay, so we have to do further analysis in order to check this out. So let's say we've got this function, absolute value of the x. And we know that if you take the derivative of this function, derivative of the function simply does not exist at the point 0, right? Because if you remember, you can take the derivative of this function, because derivative of the function is the limit, right? When, let us write this. Derivative of this function at some point x0 is the limit of x goes to the x0, f of x0 plus, so I think we have to do this with the h notation. So h goes to the 0, f of x0 plus the h minus f of x0 divided to the h. Okay? At the same point, we can find the right limits and left limits. So essentially, you can find the limit of h goes to the 0 from the right, so the same limit, f of x0 plus the h minus f of x0 divided to the h. And we can find the limit from the right, so the h goes to the, from the left, h goes to the 0 from the left, f of x0 plus the h minus f of x0 divided to the h. And if and only if these two limits are the same, then the derivative does exist. So in this case, they are not the same, because if you find the limit from the right, it is going to be plus 1. If you find the limit from the left, it is going to be minus 1. So that is why the derivative doesn't exist at this point 0. But if we look to the graph of this function, we can see that the point where the derivative doesn't exist is the local minimum point. So here, derivative doesn't exist at the point 0, doesn't exist. However, f of 0 is the local minimum, because the function is decreasing before this point and then increasing after this. So these two types of the points are very important. The points where the derivative is equal to 0 and the points where the derivative doesn't exist might be local minimum or local maximum points, and we call them as the critical points. And whenever we do look for the local minimum and local maximums, we're going to search them using these points. So a number C is called as a critical number if either derivative doesn't exist at this point, either derivative is equal to the 0. So we can see here from these two examples, what does it mean, those critical points? Okay. So now let us define what is so-called absolute maximum. So the absolute maximum is the highest or greatest value of the function in a given domain. It is something different than the local maximum. The local maximum can be any point where the function was increasing and decreasing, any hill kind of, right? But the absolute maximum should be the greatest value of the function. So let's try to find this, the absolute maximum point for the following function in order to try to understand what does it mean. So if you sketch the curve of this function, absolute value of the x in the interval from -2 to 1, you can get this kind of curve. So please note that this point here has the coordinates, the following coordinates, like -2 and 2. And this point, for example, here has the following coordinates, -1 and 1. And this point in the middle has the coordinates 0 and 0. If you remember, the 0 and 0 is the local minimum point, right? So now if you just tell me what is the greatest value for the y, right? Because we're finding the local maximum, right? What is the greatest value for the y? It's simply 2, right? And you can see here that the local, the absolute maximum is attained not at the critical point. So the critical point is when the derivative simply is equal to the 0 or it doesn't exist, right? So here, the absolute maximum is attained at the boundary, at the ending point of the interval. Okay, so this is what is called the absolute maximum, and conversely or analogously, the absolute minimum is going to be the smallest value of the function in a given domain, and we can try to do this for this function. So let's say we are given the parabola, right? So minus x in the square plus t, we're given this in the domain from minus t to the 3. So we can find the coordinates of this point here down. So the coordinates of this point here is going to be, if you substitute the 3, it's going to be minus 9. So at the point 3, it's going to be minus 9 plus 2, it's going to be minus 7, right? So at this point again, so at this point here again, the curve is reaching its absolute minimum. But again, it is not the local minimum, okay? So the local minimum can be absolute minimum, but the absolute minimum is something different than the local minimum. Local minimum is when the curve was decreasing and then increasing. The absolute minimum is the smallest value of the curve at the given domain. So now we need to discuss how to find all of the absolute minimum and absolute maximum points. In order to do this, we're going to use something which is called like a closed interval method. So let's say we are given the curve. So what we need to do first of all is we need to find all of the critical points, because we can reach the absolute minimum or absolute maximum at the local minimum and local maximums, right? So we're going to find the critical points. So for example, the critical points are going to be here where the derivatives are equal to the 0. So please note that this point should be also the critical point, which is not included here in my slides, but this is also the critical point. The critical points for this curve are the points where the derivative are equal to the 0. Then we need to also find the values of this function at the ending points of the interval, right, of the boundary, of the domain. Okay, then we have to compare all of the values at the critical points and at the ending points of the interval of the domain. Then the smallest value out of all of these 5 points is going to be the absolute minimum, and the greatest point out of all of this 5 is going to be the absolute maximum. So we can see here that the absolute minimum is here, so is one of the critical points, right? And we can also see here that the absolute maximum is going to be this point, one of the ending points. So let's try to do an example. So let's say we are given some curve, and we have to find the absolute maximum and absolute minimum in the given domain. So I'm going to do this. So let's first of all find all of the critical points. So we have to take the derivative of this function. It's going to be 3x in the square minus 4x. I'm going to take out the x from the brackets, and if I do this, it's going to be 3x minus 4. So there are essentially 2 critical points in this domain. So the x is equal to the 0 and x is equal to the 4 over 3 are the 2 critical points. So I can even say which of them is the local maximum and local minimum if I just put them into the domain, into the number line, and look for the signs of the derivative. That's going to be plus, minus, and plus. The function was increasing and then decreasing and then increasing. So it means that at the point 0, the function is reaching its local maximum. And at the point 4 over 3, the function is reaching its local minimum. So we've got, again, ending points as well. So the ending points are going to be, let me denote this as a minus 1 over 2. And b is equal to the 4. We've got 4 points to be checked. We have to find the value of the function for all of these points, and then we need to choose the one which is the greatest as the absolute maximum, and we have to choose the one which is the smallest as the absolute minimum. So let's evaluate this. What is the f of 0? It is going to be simply equal to the 1. So f of minus 1 over 2 is going to be minus 1 over 8 minus 2 times the 1 over 4 plus 1. So I'm going to give the common denominator. It's going to be 2 here and 8 here. It's going to be minus 1. So minus 4 plus 8 divided to the 8. So this is going to be 3 over 8. So the value of the function at the 4 over 3 is going to be equal to 64 over 27 minus 2 times the 16 divided to the 9 plus 4 over 3. Again, I'm going to give the, plus 1. Plus 1. Again, I'm going to give the common denominator. So the second term should be multiplied to the 3. And the third term should be multiplied to the 27. So let's do this. It's going to be 64 minus, it's going to be 32 times the 3. It's 96, right? So plus 27 divided to the 27. So this is going to be 22 minus 22 plus 25. It's going to be 5 over 27. And the last value, so at the 4, so I'm going to calculate the value just here. So f of 4 is going to be equal to the 64 minus 2 times the 16 plus 1. So this is 32, so 64 minus 32, which is 32 plus 1, it's going to be 33. Okay, so it's clear that the absolute maximum is attained here, right, at the point 33, and absolute minimum, actually, this point is the smallest, I think. So this point is the smallest. So it's attained here, okay? So the absolute minimum is attained at the 4 over 3, and this is equal to the 5 over 27. And the absolute maximum, this is the absolute minimum, and the absolute maximum is attained at the 4, and this is equal to the 33. So this is how we need to look for the absolute maximums and absolute minimums. And please note that we can find them using the local maximums and local minimums, and we can find the local minimum and local maximums using the derivatives. Thank you very much for your attention. I hope that this was helpful for you.